Welcome to this session on Pytops and SIMCET usage and training. Pytops is the software for identification of transfer function models and also for PID tuning, optimization, and design of advanced process control schemes. It is a closed-loop system identification tool with many other functionalities for the design and implementation of PID controllers and advanced process control, and also model predictive control. SIMCET is a PID tuning training simulator that makes your computer feel like as if you are in a real plant tuning real PIDs on a real distributed control system or programmable logic controller. When new engineers, or even experienced engineers, enter the control room, they are responsible for PID tuning. And the early days of their experience are often challenging and overwhelming because of complexities and safety issues in the control room. Any mistake in PID tuning could result in severe oscillations that could even lead to a catastrophic shutdown of the plant, jeopardizing their very existence in their jobs. With SIMCET, you can practice PID tuning loops, which look very realistic with noise, drifts, unmeasured disturbances, and you can play with the tuning. You can use the trial and error method of tuning to improve the tuning parameters, or you can also generate Excel data from SIMCET. It will first create CSV files that you save as Excel, and then Pytops will identify transfer functions with those files generated from SIMCET. Then Pytops can identify open-loop transfer functions using either open-loop or closed-loop data. Even multivariable transfer functions can be identified with completely oscillatory data. Once Pytops identifies the open-loop transfer function, it also has a simulator to set up the PID loop and tune it mathematically using integrated error minimization or reduced overshoot, or several other criteria like internal model control, IMC, Cohen-Kuhn tuning, lambda tuning, and also Ziegler-Nichols open loop. Let us directly dive into the software and show you how everything works. First, I am going to start the SIMCET. Let us do that. We are going to start SIMCET. This is the icon for it. Right-click, Run as Administrator, and you will see the SIMCET screen. On the left side, you have Tuning Practice, where you have a lot of chemical plants, and if you, for example, click on Refinery, then you have all these sub-menus. So let's click here. Reflux Flow Control. Now you are tuning this flow controller, and you have these drums, and you have a typical process. And the PV is the red line, which is the signal coming from this flow meter. You can see the signal is approximately 46 to 48. The blue is the set point, which is here. You can see it's 45, which is also the set point here. And it's also the set point, like displayed on a faceplate. And you can see the blue line. The y-axis is 45, which is the set point. And the green line is the output from the PID that goes to this control valve, right? You can see the control is not that good. There is some oscillation and bad control. But now you can play with it till your heart's pleased. I will just type in a ridiculously high proportional gain, which has made the controller totally unstable. If you do this in the real plant, it will cause a potential major problem or can also result in your job loss. So that is not a good idea. You can also go fast, or you can go slow. You have this blue bar with which you can adjust the speed. You can also change the simulation time. If I go to 100 seconds now, the window is much shorter, and you can slow it down. You can put high integral, or let's put really low integral to make the controller impatient. The controller is unstable now because of excessive integral action, so you can play around. You can also change the set point, put the controller in auto or manual. You can do whatever you want, which you cannot do in the real plant. Let's take a look at another example. You go to fertilizer and you have flow control there. So now you have flow control on LP section in a fertilizer plant. And the controller that you are tuning is always the blue controller or the cyan controller. You will notice there are other controllers which are brown and white. This controller is cyan and white. And the PV is the red line that you see here, coming from this line. Set point is 800. It is the blue line here, and the output goes to this control valve, and it is the green line. So this is the controller. Now we will go through an example. But before that, let me mention you the tuning tests. After you have tuned, let's say 20 controllers, and you feel you have achieved good amount of proficiency after going through the SIMCET documentation, which also provides excellent concise training on PID tuning, or better still, you can take over our PID 100 training course, which is available on our website, PiControlSolutions.com. The PID 100 training course will make you a tuning expert with all the skills and knowledge you need about PID tuning. After you finish the training and the tuning practice, then you can take tests. When you take the tests, it asks you to type in your name and you will type it here. Click OK. And now it gives you a problem definition, what loop you are going to be tuning. It also tells you the time unit on the x-axis, which is minutes. It gives you the CV range and the MV range. Remember, the CV range and the MV range impact the tuning parameters. You need to know that. Then click Continue. And now this is a randomly generated test. The blue or cyan controller, the LC, is the one that you're going to be tuning again. The set point is over here, 55, which you can see on the left side. And it is also over here, and also over here, on the bottom right. You can make the simulation go fast, or you can make it go slow, or you can be in the middle, whatever you like. And you can change the tuning parameters. You can make a set point change and collect the data. You can click on Start Data Collection and then save data when you are finished. And then SIMCET will make an Excel file. You are supposed to take all the 12 tests. This can be done in a semester course in process control as a take-home exercise, take-home test, or take-home homework. And you are welcome to tune by just manually tuning the parameters. Like, let's say, I make this integral to be 25, and now you can make another set point change and see what the response is. The green line is the PID output, the red line is the PID PV, and the blue line is a set point. There are random disturbances, noise, and drifts, and unmeasured disturbances, superimposed to make the simulation look very realistic, as if you are in the real plant. You can do your tuning changes based on trial and error, based on theory covered in PID 100 training course. Or you can start data collection, save data, and then use Pytops and mathematically compute the tuning parameters, which is what we will also show you in this video. But for now, let us say these were our best parameters. Let's also give some filter and we will submit. I may get a low score because we didn't really do any calculations or anything. I got 14 out of 100. It is not a good score. But now you can continue with the remaining tests, and after you finish all of them, you will click on Submit, and then you will be able to get your grade report. You can see here that the best value is 5. I put 0.2. Integral was also off because this is just to illustrate, and I didn't really spend much any time in tuning, so my score is only 15. When you take all the 12 tests, you will get the average score here. And this can be used by a process control professor in a college. Maybe 10 or 20% of the final examination, or the final grade, could be from this take-home exercise after the student has completed all 12 sessions. Let us go now to chemical plant, and I'm going to collect data on this flow controller. We will say Start Data Collection, and now the data is being collected. The red line is the PV, blue line is the set point, green line is the PID output. The PID output is going to this control valve. The red line the PV, is coming from this flow meter. And the set point is coming from the ratio controller, which is inactive right now. So set point is 7, which is here, which we can change. Right now we are in automatic mode. Let us make a change from 7 to 11. And remember, this data is being collected, and we can use this data to mathematically compute the open loop transfer function parameters. As you can see, there is a substantial overshoot. The red line, which is the PV, overshot the blue line, which is the set point, and there is a lot of oscillations. Let us make another set point change, back to 7. And again, remember, the green line is the PID output, which is the control valve, this control valve to be exact. And the red line is the PV, coming from this steam flow meter. Maybe we can even put the controller in manual. And now can you see, because we went into manual, the green line is flat, because controller is turned off. We can also play around a bit. We will go to 50 and see what happens. The red line is increasing because we have increased the green line. If we go to 60, the flow is increasing more. And now we can go to automatic. Now the green line is moving again. The controller is on, and we have generated some data, so let us send it now, and we can go into Pytops to do data analysis. I will say halt simulation and click on save data. The data is saved. Let us make sure that data is indeed saved. We go to the folder where SIMCET is installed, and it should be in the output directory. You can see here, today is December 11th. This is the file, SIMCET data CSV. Let's take a look at this file. Column A is the timestamp, like every second or every minute, depending on whatever it was in the simulation. This is the PID PV. CV stands for control variable, which is the process value in the PID. Set point, SP, is the set point. And MV is the manipulated variable, which is the PID output, going to the control valve. So let us save this file in Excel format, because the next software we'll be using, Pytops, does not read CSV files, it can read Excel files. I'm going to save this file and close it. I will keep the simulation open, because we are going to use the data from SIMCET and run it into Pytops. I will start Pytops now, click Run as administrator again. This is the screen in Pytops. There are two tabs here: System Identification and PID, APC Optimization. Let us first start with the system identification. First step is, you will click on this icon, which says Plant Data File. It looks like two notebooks or two pieces of paper. And go to the directory where the SIMCET file was generated. On my computer, it is located in this folder, the local disk, Program Files 86, PiControl Solutions, SIMCET version 11. And this is the file we just created. We need to specify the time now. The time was in seconds, and it is 1 second scan rate in SIMCET. We are going to use 1 second, and we generated data for 1090 seconds. That is the total length of the Excel file. As you may recall, we made a set point change. First, select your CV. This is the CV1, and CV2 is the set point, which is this blue line. And the manipulated variable is the MV, which is the control valve. As we don't have MV2, go to the bottom right and uncheck MV2. This is our controller output. And this is the PV, which is coming from the SIMCET controller. And we will now choose the model selection. It will be a custom model selection. We will use a first order. And we are going to click on Identify. That will use the data and come up with the model. And this is the model. The model is the first order model. The blue line is the first order model. The gain is 1, delay is 10 seconds, and time constant is 35 or 34. We are finished identifying, and we'll go to PID, APC optimization. We are using this equation, but we need to check in SIMCET for it. Let us look at the equation to make sure it is the same. PID equation is B0, which is this, and we will check the instrument range, 0 to 25 for the control variable, 0 to 100 for the manipulated variable. Let us now set the range 0 to 25 for the CV and 0 to 100 for the MV. Time is in seconds integral time. We click OK, and then here, use TF1, which is what we just identified from the system identification. And let's make a set point change from 10 to 12 and see what happens. Then click on Tuning. You have model-based tuning and artificial intelligence-based tuning. Let's use the IMC PI, and this is the response. The green line is the PID output, the red is the PV, and these are the tuning parameters, 0.19 and 34. If you want to be maybe a little bit aggressive, we can see how it looks like. Now we can play around. Let's see. We don't want to overshoot, so we can use 30 or 33 was pretty good. And this is maybe 0.18. So these are our tuning parameters, 0.18 and 33. And now we go to SIMCET and make it 0.18 and change this to 33, and now we can start the simulation again. Here we can put some filtering. Let us see now what happens when we make a set point change. We go to 11 and look at the beautiful response. You can see here, it is as good as it can be. Let us do one more set point change and see how it looks. You can see the PV now is going beautifully on the blue line. These are optimal tuning parameters. With that, we conclude our video on the training of Pytops and SIMCET. SIMCET is like a real plant. It will generate data like as if you are in the real plant, and Pytops will identify the tuning parameters. Hope you enjoyed the video. If you have any questions, feel free to contact us at following information. Thank you for watching this video. Goodbye.